Hey guys, welcome back to another chemistry lesson. Today our topic is going to be average atomic mass. Let's grab my fancy pen here so we're good to go. Average atomic mass. We're going to start with a little bit of a review about atoms. So when we're talking about elements, atoms, we've got the atomic number right up at the top of the square on the periodic table. It's going to tell you how many protons and electrons there are in the atom, right? Protons in the nucleus, electrons zipping around the outside. You can also use the periodic table to figure out valence electrons. So, quick refresher, valence electrons, those are your outside shell electrons. Now, they're the outside electrons. They have a special name because they're the most important ones for chemistry. They're the ones involved in bonding. So if I had to draw like what should I draw? Something small. Let's do a lithium. It's got an atomic number of 3. So it would have 3 protons in the middle. Protons. And the reason those don't all get repelled by each other is that there's some neutrons in there too. We'll talk about neutrons in a minute, but they help them kind of glue things together. And then we're also going to have 3 electrons. The first shell has 2, and the second shell can hold up to 8. So we would say lithium has 1 valence electron. Remembering all this? So far, so good? So if you look at a square of the periodic table, you'd have your atomic number somewhere, you're going to have the symbol, you're probably going to have the name, and you're going to have the atomic mass. Those 4 things are on pretty much every single periodic table you're going to find. Now, there might be a few other pieces of information here and there, but those 4 are pretty consistent for just about everywhere you go. So if you look at the periodic table, another quick review here, there is a pattern to valence electrons. Everything here in group 1 has 1 valence electron. Everything in group 2 has 2 valence electrons. And if you skip over all these weird ones, which we call transition metals, those are our transition metals. Then when you get to group 13, these have 3 valence electrons, 4 valence electrons, 5 valence electrons, 6 valence electrons, 7 valence electrons, and 8 valence electrons. Whew. And if you remember back to, actually we're probably going to talk about it shortly anyways, but the number of electrons that every element wants is 8. They always want a full shell. So anything here that already has 8, it's not going to react with anything. These are the noble gases. They're not going to have any charges. Anything with 7 wants to gain an electron. So these are all going to have a charge of 1 minus. 6 electrons means I need 2 more, so we'll have a 2 negative charge. 5 electrons means a 3 negative charge. 4 can go either way. So these ones can be kind of tricky to tell what the charge is going to be. Is it going to be a plus 4? Is it going to be a minus 4? And you'll notice you don't see a lot of these in the elements we talk about. Well, okay, the transition metals we do. But these top 4, you don't see that often. They literally have their own branch of chemistry. Carbon is organic chemistry because of the fact that it can bond plus or minus 4, makes it kind of special. It can do all kinds of cool stuff. If we come over to this side of the periodic table, the far left, these things already have an electron. The easiest way for them to get a full shell isn't to gain 7 more, it's actually to get rid of it. So these ones have a charge of a positive. This would be 2 positive, and these would be 3 positive. So this should be all review stuff, but a quick little crash course on number of valence electrons and charges. Transition metals are so large, and they're semi-stable states, which we can talk about more if you take grade 12 chemistry. But because of these are all being large, some of them have, well, most of them actually, have multiple charges. So like iron could be a plus 3, or it could be a plus 2. And the only way to tell is through looking at what it's matched with or through a naming convention. And we're going to talk about naming today as well. All right, so there's our crash course review of valence electrons and atoms. So mass number. The mass number tells you how many particles there are in the nucleus. So that would be protons plus neutrons. So your mass is just your protons plus your neutrons together. Now it will never include electrons because their mass is so very small we just ignore it. It's basically 0 compared to what a proton weighs. It's like if you're weighing elephants, I got 5 elephants and there's an acorn on the scale, I can ignore the acorn, right? Those 5 elephants are going to be way bigger. So we ignore the electrons. They're like the acorns. They don't matter. Too small. A common way to write elements is using what's called nuclear notation. Now, this might be new. I'm not sure if you guys did this last year. You write the symbol for the element. On the bottom, you put atomic number. And on the top, you put atomic mass. And if you're ever forgetting which number is which, atomic number is always the smaller number, and it's always the lower number. It's always on bottom. It has to be smaller because it's protons plus neutrons, right? So the mass is always going to be bigger than the atomic number, because the atomic number is just protons. The atomic mass is protons and neutrons. So how many neutrons then does this element have? So this is carbon 12, carbon with a mass of 12. So carbon, mass of 12, I'm going to use this formula right here. Mass of 12 equals protons plus neutrons. Now I know the protons are 6 because of the atomic number. So 6 plus what gives me 12? Well, 6. So I've got 6 neutrons. So you always got to remember the protons and neutrons together give you the mass. Isotopes. Whoops, meant to capitalize this one. This is a big title. Isotopes. Isotopes are elements that have a different number of neutrons in the nucleus, even though it's the same element. Many of them occur naturally. So example, we just looked at carbon 12. That's the most common isotope of carbon. But carbon also has an isotope with a mass of 14. Now we know it's still carbon because the atomic number hasn't changed. It's still 6. But now it weighs something different. So an isotope is the same element with a different weight, a different mass. Which means if you haven't changed protons, what have you changed? Number of neutrons. It's the only thing you can change if you want to change the mass, because electrons don't count. So often isotopes are written with their name, the name of the element written out, and the mass number only. So for example, we would literally call it carbon 14, and you would see it written just like that. Sometimes people shorten it to C14, but a lot of times it'll just be like carbon 14, or they'd write it as nuclear notation. So all kinds of different ways to represent elements now. The number is the mass, because if you say carbon, you know right away it has to have 6 protons. You can't change the atomic number. If I change the atomic number, if I make this a 7, well, I'm not carbon anymore. I would be whatever's atomic mass 7. Is that nitrogen? Yeah, it's nitrogen. So you can't change the atomic number, you can only change the mass. And so that's why they write the mass number beside it. Speaking of mass, what do we measure it in? Well, atomic mass units, as you can probably tell by the title of this slide. An atomic mass unit is 1/12 the mass of carbon 12. This is the important part of this slide. If I were you, I would not write down the rest of this. If you paused it and wrote down the rest of it, well, it's never bad to have more knowledge, right? So this is just a little background on the atomic mass unit. You're not going to be tested on this. I just think it's really cool and interesting, so I'm sharing it with you. The atomic mass unit was originally based on oxygen. Oxygen's everywhere. All kinds of things bond with oxygen, so it's pretty easy to measure. So they would say one atomic mass unit would just be 1/16 of oxygen, because oxygen weighs about 16. However, chemists and physicists ended up with different atomic mass units, because chemists would use natural oxygen. I'd put an element out, I would let it oxidize with all the oxygen in the air, some of which was oxygen 16, some was oxygen 17, some was oxygen 18. So I had a mix of these different oxygen isotopes. Physicists were doing something called mass spectrometry, which requires a very specific measurement. So they would take only mass oxygen 16 and then divide that by 16. So you can see that you'd end up with 2 different numbers. One based on just whatever oxygen 16 weighed, the other based on the average of however many oxygen 16s, 17s, and 18s occur naturally in the world. So we got 2 different disciplines, chemistry and physics, both calling it an atomic mass unit and both being different numbers. That's a problem. So they want to fix this. They originally talked about using hydrogen because it's the smallest, right? Just call hydrogen 1 and we'll go from there. The problem was switching hydrogen to 1 made the chemists' numbers way off. Because they had an average here of these 3 different isotopes, if you switch to the hydrogen one, all of your numbers are off. And that's going to screw up a lot of existing work. So everyone kind of agreed, we'll need to find something in the middle. and they ended up switching to 1/12 of the carbon-12. So the chemists kind of bit the bullet, said, fine, we won't use natural carbon. We'll use only the carbon-12 isotope. And that made the physicists happy. And they also managed to be a less drastic change from the oxygen, or from the hydrogen system, sorry. So it was a little different from their oxygen average, but not enough that would make a big difference. And so the chemists were okay with that. And so all masses, this part is important, all masses on the periodic table are measured in atomic mass units, and they are the average mass. It would be however much oxygen, 16 plus 17 plus 18, you divide that by however much you got, you can figure out your average mass. So if I know how many atoms of the different isotopes there are, you can calculate that. This helps identify how heavy a sample is. You can tell if it's got a lot of oxygen 18 in it, for example, if you weigh it and it's heavier than average. So let's take a look. I'll show you guys this calculation because it sounds scary. It's actually pretty easy. Elemental boron has 2 isotopes. Let's start with 2. You can go up to as many as you want, but we'll do 2. We got boron 10, which has a relative abundance, that means how much of it is out there, is 19.78%. So of all the boron I can find, on average, 19.78% of it will be boron 10. There's also boron 11, which has an abundance of 80.22%. Calculate average mass. And so you could do as many of these isotopes if you want. If something had 8 isotopes, you could do 8 isotopes. As long as the percents add to 100, you're good. And so here's your formula. If I want my average mass, I take the mass of the first isotope, so in this case, it weighs 10, times the abundance, 19.78%, and then I add it to the other one. It's 11 times 80.22%. Now, I hope some of you guys are scratching your heads right now, because there's one rule of math I just broke. You never, ever, ever do math with percents, right? You can't use a percent in math. We have to convert that. So you change the percent to a decimal by moving the decimal twice. You divide it by 100. Plus 11 times 0.8022. All right. So if I do this times 10, well, that's an easy enough one. I just move the decimal back one spot. Plus, grab my handy dandy calculator, 11 times 0.8022 gives me 8.8242. Add those two together, and I get 10.8022. All right. So that is the average mass of a boron. Now, does that number make sense? Well, some boron is 10. Most of it is 11. So my answer should be between 10 and 11 and probably closer to 11. Is this answer between 10 and 11 and a little bit closer to 11? Yeah, it is. All right, that makes a lot of sense. And if you check a periodic table, you'd probably see that the mass of boron is pretty close to that too, within a little bit of a rounding error, depending on the precision of how you calculated that number. Oh, I should probably do significant figures, hey? I got 4 significant figures there. I don't know what the mass is actually measured to, so I'm going to pretend it doesn't have significant figures for today because I don't know how precise that actual mass is. Maybe, oh, actually, it should be exactly 10. 10 protons plus neutrons. So if that's an exact number, it wouldn't really have a precision. So let's go 4 significant digits. We'll use the percent for that, 80.22 and 19.78. All right. Quick review. How do we name things? So that kind of wraps up our mass section. We're going to talk briefly about naming, and then we're going to call her a day here. So naming. And we're only going to look at ionic compounds. So first of all, what the heck is an ionic compound? Well, ionic compounds are anything that bond by lending electrons or stealing electrons from each other. They're almost always metal and non-metal together. So NaCl, for example. Sodium has 1 valence electron. Chlorine, being a group 7 at the very end there, has 7 valence electrons. So for chlorine to be happy, it wants 1. For sodium to be happy, it wants to get rid of 1. So it's going to transfer, and you'll be left with sodium, who lost an electron, so ends up with a positive charge, and chlorine, who gained an electron, so he's now happy, but he has an extra electron, so he's got a negative charge. And they're held together because positives and negatives attract. So they have, sodium has lent its electron to chlorine, now they're both charged, they form a compound. We call that an ionic compound. So how do we name it? Well, let's start here. Elements always want a full or empty shell. We talked about that. It's called the octet rule, 8 being oct. If the metal is a transition metal, remember that the name has to be written with a Roman numeral after it. That's going to tell you what the charge on the metal is. We're going to get some examples of this later, but for now you could see like lead 2 chloride means the lead has a 2+ charge on it. Iron 3 oxide means the iron has a 3+ charge on it. Another review here, the polyatomic ions. Those are substances that have more than one element bonded together, and they travel usually as a group. And they will have one charge together. They behave the same as other single ions. So for example, ammonium is NH4+. So I could put ammonium together with a chloride. One positive and one negative, things would be happy. So this would be ammonium chloride, and that would work. The NH4 acts as if it's a single entity. The nitrate ion is a negative one. I could take sodium with a +1 charge, and I could combine it with nitrate, which is an NO3, because it has sodium is a positive, nitrate is the entire thing has a charge of -1. So those are polyatomics. Anytime you see more than two uppercase letters, more than 2 atoms, one of them is going to be part of a polyatomic. When naming ionic compounds, 2 steps. You name the first substance. Just you take a look at it, the positively charged thing, what's the name of it? You write that down. And then you have 2 possibilities, 2A and 2B. 2A, if the second substance is just an element, you use its name, but change the ending to IDE. So I named the first one, sodium. Second one is an element, instead of chlorine, I change it to chloride. This would be calcium bromide. And this would be aluminum oxide. Doesn't matter about the numbers because we know what the numbers will be from the charges. You don't have to write anything with the numbers, just aluminum oxide. Now there's a second case. If the second substance is polyatomic instead, you don't have to add IDE, you just use its name. So this is potassium, and NO3 is nitrate. I'll make sure I get you guys a excuse me. I'll make sure I get you guys a copy of the polyatomic sheet so you have the names with you. This would be hydrogen. SO4 is sulfate. You end up using these enough, you eventually have them memorized, like the common ones. But for now, I'll get that sheet for you. And finally, we have magnesium. That's the metal. That's the first one. And it's matched with phosphate. Magnesium phosphate. One thing you might be noticing here is that these chemicals are not written correctly. Like obviously that one should be Mg2 PO little 4 little 2. Unfortunately, this app for doing notes doesn't allow you to do subscripts very easily at all. So you're gonna have to get used to seeing the numbers in the middle. It looks really ugly and it drives me nuts because this right here, magnesium phosphate, is way prettier. But unfortunately, that's the constraints of the system I got. Anyway, pop quiz. How many of each atom are here? So how many magnesiums do we got? Give it a shot. How many phosphoruses? And how many oxygens? What do you think? Pause the video and give it a shot. All right, so I'm going to count them here. I can see the little 2 for magnesium. That makes it easy. Now here's the tricky part. I got a 2 here, and it's touching the bracket. So what does it apply to? Well, it means I have 2 copies of everything in the brackets. I have 2 PO4s. So I have 2 P's and 8 O's. It's just like multiplying. You open the brackets in math, same kind of idea. If I have 2 PO4s, I have 2 P's, and I have 2 sets of 4 O's. So I'd end up with 8 oxygens in total. So that should be a bit of a reminder from last time. Also, one last thing you got to remember, don't forget to check if your first metal is a transition metal. If it is, you got to add Roman numerals in. You can tell what the charge is or what the Roman numeral will be by checking the total negative charges it is paired with. So what I mean by that is, here I've got copper, and I've got oxygen, so it's copper oxide, right? Easy. Oh, but copper is a transition metal. It's right in the middle of that periodic table. If I head back here, where's my periodic table? There it is. Where's copper? Here it is. It's in the middle of my transition metal section. So you gotta be careful. I don't know the charges. What was it paired with? That chemical was CuO, paired with oxygen. What charge does oxygen want to have? Well, oxygen should have a 2 minus. So if oxygen is a 2 minus, and the whole thing is a 0, what do I need here? 2 minus plus what gives me 0? Hopefully you figure out that should be 2 positive. So this charge has to be 2 positive to balance out the 2 negative, which means this is copper 2 oxide. Let's do a harder one. I got iron oxide. Now, iron definitely is a transition metal. I know I need to put some kind of charge in there. What's it going to be? Okay, so to tell, I look at this side. Let's start there. I got 3 oxygens. Each oxygen wants a charge of -2, so this side has a total charge of -6. If this side is -6, then this side has to be +6, right? So is this iron 6? Not quite. That +6 is split between 2 irons. So each individual iron is only going to be a +3. So I have 2 sets of +3 balancing 3 sets of +2. +6, -6, we're all balanced. Life is good. So that's how you figure out what your Roman numerals will be. Last one. I want you guys to give this one a shot on your own here. I got titanium. Gotta actually spell the whole word. Oh, there we go. There we go. Titanium something oxide. So again, pause the video here real quick. Give this one a shot. What do you think the charge should be? All right, so let's step through it. I got titanium, I got oxide. I know oxygen has a charge of -2, but I have 2 of them. So my total on this side is -4, which means titanium would have to be, well, there's only one of them, so titanium has to be, that's a titanium 4. That titanium must have a +4 charge on it in order for this to balance. So that's a titanium 4 oxide. So that's your review of average atomic mass and what masses are and the structure of the atom really briefly. And we talked a little bit about ionic naming conventions and how to do that stuff. And that's it for today. So hopefully that's all you need to know. You've had a chance to review and this is all coming back to you, but we'll definitely get a chance to practice soon. Thanks for watching, guys.